This video is sponsored by Brilliant. Hi guys, welcome to Amateur Chemistry. So in today's video, I am going to be using a lot of stinky chemistry and a microwave to turn my pea along with some lemons into the cutting edge of chemical innovation, which are quantum dots. Quantum dots are a relatively new branch of chemistry and physics. They are incredibly useful and have a wide range of possible futuristic applications. They actually have so much potential that the scientists who discovered them were awarded this year's Nobel Prize in Chemistry. Quantum dots, despite having a really fancy name, basically boil down to being very small particles of a semiconductor that act pretty much like individual atoms. Despite often being composed of thousands of them, they are so small in fact that a good part of their properties is determined not by their chemical composition but by their size. They have a lot of interesting optical properties because due to being so small, they can interact with light in a pretty weird way that has a lot to do with quantum mechanics. They can act similar to fluorescent dyes and produce beautiful colors when exposed to UV, but unlike fluorescent dyes, the color emitted by them largely depends on their size. Smaller quantum dots tend to produce blue light and larger ones red. Due to this property, they find use in a lot of optical applications, like in solar panels or displays, and if you have a QLED screen, you are using them to watch this video right now. There are many types of quantum dots, each one having a different chemical composition. Many of them rely on toxic and dangerous elements, such as cadmium or tellurium, and are rather bad for the environment, so I won't be making them today, and instead, I will focus on the more recently discovered carbon quantum dots. They behave very similarly to the other ones, but are much more environmentally friendly, and it turns out that a certain kind of them can be made with some common and very accessible chemicals, and today I will try to make some out of my own pea. It's possible because human pea contains urea, which is a byproduct of protein digestion, and it just so happens that it can be used to make some beautiful quantum dots. However, to perform the synthesis it has to be rather pure, so I can't just use my pea on its own, and I have to extract the urea from it. It shouldn't be too hard, and the main problem will be just the smell, because let me tell you, through this whole project I made my lab smell so bad that now it is hard to survive more than 5 minutes in it without wearing a gas mask. To start the extraction, I of course had to get some pea, so over a few months I collected it and managed to end up with a pretty considerable amount in this large container. I tried to drink less water and eat more protein to make the pea more rich in urea. Also, due to sitting in this container for so long, it turned brown, and as soon as I opened the lid, I was hit with an incredibly awful smell. The fermented pea smells like 10 of these plastic public toilets combined, and just this made me pretty worried about what will come next. And speaking of that, now it is time to do the most smelly part of this whole project, which is boiling the pea down to concentrate the urea and break down any proteins. I originally planned to do it outside to stop the smell from coming into my lab, but it just so happened that nature didn't want to smell bad either, so it started to rain, and that meant that I would need to do everything inside. I firstly haven't thought much of it, but it later turned out to be a big mistake. To begin the boiling, I got this big steel pot which I will to sacrifice and poured all of the pea into it. Its amount was suspiciously ideal for this pot. If I had to guess, I had about 4 liters of it, and to boil it down, I got this rusty electric stove that somehow was missing a leg, which I fixed with this piece of brick and began heating the pea. As it warmed up, the smell was still quite bearable, because my fume hood was quite good at picking up small amounts of it, but when the pea started to boil, the fume hood just gave up. After some time, the pea developed this lovely foam, which was composed mainly of its proteins. I periodically scooped it out using a spoon, and where no more appeared, I left the pea to concentrate overnight. When I came back, most of the water was gone. To evaporate out the rest, I set up this fan, which really sped up the process, but also made the smell travel far away from my fume hood, and it was so bad that I couldn't smell it anymore. I have literally destroyed my sense of smell by being near this spot for so long, which is honestly quite an achievement. When there was about a liter of the pea left, I transferred it into a flask and then into a beaker on a hot plate to continue boiling it down. I also moved everything into a different fume hood, which is much better than the previous one, and I really hoped that this smell won't be as bad as it was. You also may notice that my hot plate is now covered with aluminum foil, which prevents it from being constantly destroyed by spilled chemicals. This is actually a really good lab technique, and a big thank you goes to the person who recommended it. Anyway, while I wait for the pea to concentrate, let me tell you about a good chemistry supply shop that provides me with many chemicals, BM Chemistry. BM Chemistry sells a lot of hard-to-get chemicals of high quality, along with laboratory equipment, glassware and lots of other things, and I recommend you to check out their page, to which I provided a link in the description. Okay, now back to the pea. All of the boiling took much more time than I would like it to. I spent a better part of a week doing it, and I have more gigabytes of footage of me boiling my pea than all of the other project clips combined. After all the struggle, I was left with around 200 milliliters of some extremely concentrated pea, which smelled very weird. It was incredibly bad and honestly pretty hard to describe. The pea still has a lot of proteins and undesired salts in it, and to remove them, I have to carry out a vacuum filtration. When I got my vacuum pump, I noticed that despite the engine running, it didn't create any vacuum, so to check what caused this, I opened it and saw literal crystals of something blue on its walls. I was really confused and worried that I had lost this pump for good, but then my dad came along and fixed it for what felt like 1,000th time, and now it's running like it's new. To filter the pea, I first got it from this sealed container, which was there just to contain the smell. I then set up my vacuum filtration apparatus and began filtering the pea. At first everything went smoothly, but after some time the filter started to get clogged. The pea also somehow started to escape into my fume hood and smelled just dreadfully. After what felt like years of filtration, I now had some crystal clear concentrated pea, and it's finally time to start separating out the urea. I could theoretically try to crystallize it now, but it would be way too dirty for the quantum dot synthesis, so to purify it, I first have to convert it into a chemical called urea nitrate. It has much lower solubility in water than urea, so it will be much easier to crystallize out, and what's interesting is that it just so happens to be a pretty potent explosive. To make it, I slowly added about 80 ml of 83% nitric acid that I made from fertilizer in a previous video to my concentrated pea. The addition generated quite a lot of heat and made everything foam up a lot. It also made the smell even weirder than it was before, and now the mixture doesn't smell like pea at all. To make the urea nitrate crystallize out, I put the mixture into a fridge overnight, and when I came back there was a nice amount of small crystals on the bottom of the beaker. To separate them, I again used vacuum filtration. It was now much faster than before and left me with some impure urea nitrate, which kinda looked like dirt. As the next step, I have to convert it back to urea, and I can do that by reacting it with a base such as potassium carbonate, which will convert the urea nitrate to urea, potassium nitrate, carbon dioxide and water. I dissolved my urea nitrate in some distilled water, and when the solution was clear, I proceeded to slowly add a concentrated solution of potassium carbonate. The addition generated a lot of carbon dioxide, which caused a ton of foam to appear. At one point it nearly overflowed, and because I didn't want to repeat the sodium acetate incident, I transferred the mixture into a metal pot and added the potassium carbonate solution until the foam stopped appearing. I am now left with an impure solution of urea and potassium nitrate, and to proceed, I evaporated out most of the water using a hot water bath to not break down any of the urea, and in the end I was left with this weird sludge which quickly solidified into this orange cake of urea and potassium nitrate. I could actually already see some of these thin and needle-like crystals of urea on the sides of the beaker, which was really nice. The smell coming off them was just incredibly bad and interesting at the same time, because I haven't smelled anything quite like this in my entire life. To separate the potassium nitrate from urea, I'm going to take advantage of the fact that urea is really soluble in hot ethanol, while potassium nitrate is not, and to start, I heated some 96% ethanol until it started to boil and then poured it onto the orange cake. It quickly dissolved the urea and left a yellow solid floating around that should be the insoluble potassium nitrate, which I quickly removed using vacuum filtration. I then passed the filtrate through some cotton because it was still quite cloudy, and in the meantime I came back to the crude potassium nitrate that I recovered and thought that it would be nice to purify it. So I quickly recrystallized it from water and got these nice brown crystals, which I then mixed with some sugar and ignited for some nice smoke. When I came back to the urea solution, it looked much better and kind of reminded me of apple juice. I now have to evaporate it down, so I got it onto my hot plate and boiled away the ethanol. When about half of it was gone, I got the mixture of the heat and put it into a freezer to crystallize out the urea. When I took it out, instead of nice crystals, I got this orange cream, which I vacuum filtered and recrystallized using water and ethanol, hoping to get some pure urea crystals, but instead, I got this weird slurry. It means that there are still some impurities present. I could do a second recrystallization to remove them, but it would make my yield even worse than it already is, and I figured that for making the quantum dots, I don't need the urea to be super pure, so I just vacuum filtered the mixture and ended up with these wet orange crystals. They don't look like much because, well, they aren't. If I would want to get some more, I could boil down the filtrate because there is still a lot of urea in it, but I only need a small amount of it for the quantum dots, so I just didn't bother. I put the urea into an oven to dry on low heat for a few hours, and in the end it turned out that I set the temperature up a little too high because the plastic petri dish partially melted. The urea now looks like this orange crust. To measure its amount, I scraped it off the plastic and put it onto a scale, and it turns out that I managed to get a whopping 10 grams of it. This yield is honestly just bad. It is impossible to calculate its percentage exactly, but I hope to get at least twice as much. My urea is also pretty impure and probably a little wet, but besides all that, now that I finally have it, I can begin making the quantum dots. For their synthesis, apart from the urea, I am also going to need some citric acid. I could of course just use some store-bought one, but I wanted my quantum dots to be made from natural chemicals as a proof of concept, and it just so happens that citric acid occurs naturally in lemons. It can be extracted quite easily, and I showed how to do that in the lemons to chloroform video, and now I was ready to extract it for a second time, but then I remembered that I still have the filtrate from the citric acid crystallization I did in that video. It miraculously survived in my fridge for 5 months, and now it was the perfect time to take it out. Its inside looked rather black. I expected that I would have to boil it down to concentrate the citric acid, but to my surprise, there were already some really nice crystals of it in the beaker. I put them onto a towel to dry. They were a little contaminated with this black powder, but compared to the urea, they were incredibly pure, and I was just really happy that I found them and not, for example, thrown them out, especially because I originally didn't want to use them for anything. Anyway, now I can finally make the quantum dots, and to start I have to mix my urea with the citric acid in a roughly 2:1 ratio. To do that, I weighed out 1 gram of urea and 0.5 grams of citric acid on a petri dish. I then ground them together with my new and yet unbroken mortar and pestle, which I was able to buy because of a very generous donation made by a viewer. When I was done, the mixture ended up turning into a slurry because urea can pull a lot of moisture from the air. With my starting material ready, I can begin the actual synthesis. I will have to use a pretty unusual tool, which is a microwave. I brought the cheapest one that I could find and put my own logo on top of the original one. I will use this microwave in a lot of future videos, and I named it the Science Oven 5000. I then assembled the spinning glass thing inside of it and got back to my urea and citric acid mix. To make the quantum dots, I got a small amount of it along with some distilled water into a test tube, and then put the entire thing into the microwave and turn it on. I know that it's difficult to see through the steel mesh of the microwave window, but as time went on, more and more water evaporated to finally leave a small amount of molten urea and citric acid in the test tube, which progressively got darker and darker, indicating the creation of quantum dots. The reactions that are going on here are really complex. Firstly, most of the water evaporates, making an extremely fine mix of citric acid and urea, which under high heat in microwaves can pyrolyze and bond together to form large structures, which are the quantum dots. They consist of various types of bonds between the carbon atoms and lots of amide groups provided by the urea, which make them not coalesce together and become water soluble. The point of doing this whole thing in the microwave is that it is cheap, efficient and fast, while the traditional methods require the use of very high temperatures and often an autoclave, which makes microwaves a really good replacement. Anyway, when the reaction finished, I took the test tube out of the microwave, and as you can see, the final product is this brown sludge, which consists of an ungodly amount of various quantum dots and some unwanted byproducts. The quantum dots don't look like much when they are that concentrated, but when I get my good old UV lightsaber and dilute them with some water, they start to grow a nice lime green color, which kind of reminds me of fluorescein, and under normal light, they look like this yellow water. When I poured some of it into a beaker with distilled water under UV light, the effect was really beautiful, and I couldn't stop at just that. I also made a forbidden Dr. Pepper and got some nice shots of the quantum dots in a graduated cylinder. The quantum dots work by absorbing high energy photons of the UV light and converting them into some lower energy ones that often end up in the visible spectrum. The dot's efficiency, or so-called quantum yield, is dependent on many things, such as their composition and the solvent that they are in. Their color greatly depends on their size, but when it comes to the carbon quantum dots, the types of bonds made by the carbon also have a big impact on the final color. In theory, by adding different chemicals to the starting material, I could change the amount of certain types of bonds in the quantum dots, and that should result in a color change. I really wanted to make some red ones, and I read in a paper that they can be made by the introduction of formic acid to the reaction, and to test that, I repeated the previous procedure with 80% formic acid instead of water, and the results were, unfortunately, exactly the same as before. I also tried this with acetic acid, but that didn't do anything either. I suspect that's because the microwave made the formic and acetic acid boil off before they could react with anything, and to fix that, I would have to use a sealed and high pressure container, which I unfortunately don't have. I tested the procedure with a ton of different things to see if I can make any more colors, but in the end I concluded that only green quantum dots can be made from citric acid and urea using a microwave and test tubes, which is quite sad, but don't get me wrong, because just how freaking cool is that I can make these fluorescent molecules with tons of futuristic applications using my pea and lemons. To further test out my quantum dots properties, I made a lot of them using about half of the starting material in a vial, and this time I wanted to let them dry to see if they would be still fluorescent, so I poured them into this crystallizing dish and let the water slowly evaporate over a few days. When I came back, the quantum dots look like these black taro things. In this form they don't fluoresce at all, but when I dropped some water onto them, the fluorescence quickly came back. In this tar form, they are also incredibly potent, and just a tiny amount is capable of making 1.5 liters of water fluoresce really strongly. For the next experiment, I wanted to see how the quantum dots behave in different solvents, so I got a few vials and filled them with a few milliliters of almost every solvent that I have, and then introduced about a drop of concentrated quantum dots into each one. As you can see, the solvent really has an impact on the quantum dots color, meaning that they are solvatochromic. They are unfortunately unable to dissolve in non-polar solvents like DCM or toluene, because these amide groups attached to them are really hydrophilic. I replaced the non-polar solvents with some ammonia and hydrochloric acid to test how the pH affects their color. The ammonia worked well, but the hydrochloric acid destroyed the fluorescence, so I swapped it for some acetic acid, which worked much better. Of all the solvents, the MSO worked the best. It made the dots take on a nice turquoise color that was very bright, and I was really pleasantly surprised by how nicely the dots looked in some of the solvents. And now, after all of this, I wanted to answer the most important question, and that is, do quantum dots make a good paint? Well, it turns out that they can make something fluoresce really nicely when applied in small amounts. They also become almost invisible after drying, which makes them a good candidate for an invisible ink, and I think that it would be really cool to see someone painting an actual piece of art with them. I also wanted to test if carbon quantum dots can be made from easy-to-access materials other than citric acid and urea, and I read somewhere that microwaving a solution of sugar and sodium hydroxide also works, so I did just that, but unfortunately the dots weren't exactly bright and they looked just dirty, but on the upside, their synthesis is just incredibly accessible. Anyway, I think that this project was a really nice one. In the future I will try to do something actually useful with the quantum dots, because they are such a cool thing that they deserve some more attention. And you know what's also really cool as well as completely free and easy? This video sponsor Brilliant. Brilliant is an amazing way to learn STEM subjects like math and data or computer science. It is an interesting and fun way of solving complex problems in thousands of interactive lessons personalized to suit your own learning pace. For example, their amazing How Technology Works course that I personally took teaches you about what makes a password good and how computer memory works, among many other interesting things. To try everything that Brilliant has to offer completely free for a full 30 days, visit brilliant.org/amateurchemistry or just click the link in the description. The first 200 of you to sign up using my link will get 20% of Brilliant's annual premium subscription. Anyway guys, I hope that you like this rather stinky project, and thank you very much for watching. Like and subscribe if you enjoyed the video. Also, as always, big thanks go to my Patreons, especially Isaac Von Liu and Dangerous Lab, as well as R2D2, Riley Reprogul, Joseph Kuddy, M.I., William Bradley and Unitrate. If you would also want to support my work and gain access to some exclusive content, you can consider becoming a Patreon, and see you guys in the next video.